That's okay. So let me introduce you now. Okay. So we are very happy to have Professor Ogawa from Meiji University. He is an expert at the reaction diffusion system, and also now you are a dean, right? So very busy.
Yeah.
He's very busy, and after the talk, he will have a faculty meeting. So please prepare quick question. Okay, so today his talk title is Invasion to the Buffer Zone Between Two Strong Species. Let's welcome him.
Thank you very much. I'm very glad to for the invitation of this NCTS seminar on the nonlinear evolutionary dynamics. I appreciate it very much. And of course, I have many friends in Taiwan. So, but still, unfortunately, I have no chance to really meet each other. So, I like to discuss by using this kind of online talk. So that's why I'm very glad today. Well, let me expand the screen. And can you see my first page for the whole screen, right?
Yes.
Okay.
Yes.
Okay, so so before going to start my talk, I need to explain the progress of this research because I have studied this kind of program for many years, say 7 or even more years. And at the very beginning, we had a discussion between Professor Chun-Chan Chen and Li Chan. So that was really the starting point. And after that, maybe 4 or 5 years, we completed the main theoretical part of this research. But I was struggling. There is a kind of inconsistency between theoretical part and numerical simulation. So finally, Professor Hideo Ikeda, one of the collaborators, came to Tokyo to insist me to concentrate on the study of this topic, say 3 or 4 days. That was March 2020, last year. And after the daytime discussion, we drank much in Nakano area, Japanese local pub. That was right before the first outbreak of COVID-19 in Tokyo. But luckily, we are quite safe to escape from the COVID-19. But anyway, and so at that concentrated discussion between Hideo Ikeda and me, we solved the inconsistency between theoretical part and numerical part. And we after that, we have completed the finishing the paper, finishing the manuscript last September. And we explained the detail to Professor Nimura, let me say Mayan from now. But of course, last year, we can't meet. We can't really meet, and Mayan is not acquainted with online meeting. So it takes a little bit more time. And finally, he says, February this year, we had a final meeting, online meeting between Mayan. And he says, okay, so the result seems to be very interesting and very important. But the introduction is not good. So he says he's going to rewrite the introduction of the paper. So that was a final discussion with Maya. And finally, April this year, April came. So anyway, so that's why we took a little bit long time to complete this topic. But anyway, so let me start. Of course, so this research is based on the relating to the mathematical ecology. So mathematical ecology basically motivated by the naive questions So why there are so many species on Earth? And how does the ecosystem is succeeded to make a balance, very delicate balance? So how does such a balance come about? Or why are different species living while separating? So these kind of naive questions motivated mathematical biology, mathematical ecology program, and there are so many interesting results. And the key issue is, of course, coexistence and segregation and invasion, or small survival, I should say. And this invasion is going to be the main topic today. Okay, so let me first describe a very brief history of mathematical ecology. So, of course, we have started from the ODE models, say Malthus model or Bell-Hurst model. People sometimes say logistic equations, and so these are, of course, a very simple one species ODE model, and we also consider two species model by using the Lotka-Volterra. Two types of Lotka-Volterra equations. So one is a prey-predator model, and one is a Lotka-Volterra competition models. So basically, we would like to consider the, say, for example, coexistence by using these kind of Lotka-Volterra type models. And of course, a prey-predator, by using prey-predator model, we can see some kind of coexistence between prey species and predator species. But in the case of a competition case, so Gauss's law of competitive exclusion says that actually, when by only studying this ODE model, Lotka-Volterra competition model, we cannot explain the coexistence. So people need to consider PDE models corresponding to these original ODE models. So there are, of course, PD models corresponding to one species or two species. And in the case of two species model, we already know there exist traveling wave solutions. But traveling wave solutions does not really explain the coexistence, because some kind of a front wave always moving to right or leftwards. So we can't really see the coexistence. And people consider by using also a fast reaction limit, and then they are succeeding to say something about the metastability of the coexistence situations. And also, sometimes we also consider the three species model to explain coexistence or segregation in the situation by using the two predator plus one prey model, or one predator plus two prey model, or three competition species models. So today's topic, I mainly focusing on this three competition model. Okay, but before going into the detail, let me start at the beginning. Very simple reaction diffusion, one species model. But can you see and can you hear my talk?
Yes, very clear.
Yes, yes.
In my screen, just my slide, I can see just my slide, and there are no people around there. So
No problem.
kind of okay. Anyway, so if you have some trouble, I mean, the hearing was in the screen, so please say something to me. Okay. Okay. So let's consider this scalar reaction diffusion equation. So this is, of course, using the logistic type equation. And so maybe we can say easily, when the So R is, of course, a growth rate. When the growth rate R is negative, of course, there are no chance to survive for this species W. But when R is positive, we know there are kind of hair trigger effect. So when R is positive, if W is living only a tiny, small amount of population, then they are going to grow. And so shares are all over the spatial directions. So we call this hair trigger effect. Of course, but this is only, so this is because we only considering the scalar logistic type reaction diffusion equations, but the situation is not simple. And so maybe that, maybe the exotic species, so the strategy for the exotic species is something like this. So they need to find some suitable areas. So suppose there are, so suppose this kind of situation. So we consider this a little bit different type of scalar reaction diffusion equation. So now phi of x is, I call an environmental factor. So if the shape of phi is something like this, so then, so can you see my pointer? Yeah.
Yes.
So I'm just pointing around this area. So suppose phi, the shape of phi says that the environment of this situation is a little bit better compared to these tail part. So the strategy of this species W is finds a favorable place and then find a chance to survive around these areas. So let me be more precise. So of course, still phi, so still R is 0. So then there are no chance to survive. But maybe they tune their growth rate a little bit larger and larger. So then, for example, in this case, so here you see only this area, the growth rate, total growth rate is positive. So there may be a chance to survive at this area. So in the bifurcational terminology, we can expect there may exist a critical number R0 such that W has a chance to survive, or R is larger than R0. But how we can know or how we can prove these kind of things mathematically? So of course we consider the linearized equation around 0 of this equation. So because by linearization we obtain this kind of operator. So I call this L of R is an operator depending on the growth rate R. Okay, and now lambda 0 is a maximum eigenvalue for this operator for L of 0. So this is still an assumption. Okay, so then we can conclude that lambda 0 should be negative by this kind of a variational argument because phi is negative. So it is equivalent to say that L of minus lambda 0 has 0 eigenvalue with the same eigenfunction. You see? So I already say L of 0 has eigenvalue lambda 0. So we so it is of course equivalent to this equation. So that means that L of minus lambda 0 has 0 eigenvalue with the same eigenfunction. Is that okay? And we already know lambda 0 is negative. So therefore, R0 is equal to minus lambda 0. It's the critical growth rate. Okay? So here is, so as I already told you, so this operator L of R should have an eigenvalue. So, and this is an assumption. But here is an example which satisfies that assumption. Okay, so suppose phi x is minus 6 times tangent hyperbole squared. So it has eigenvalue minus 2. So therefore, if I put R02 here, so then it has a 0 eigenvalue, which is given by 1 minus tangent hyperbolic squared. So this can be checked by a simple calculation. Okay, see, so phi is, so I drew a shape of phi x and R0 plus phi x here. So in this situation, we have a chance, so W has a chance to survive like this shape, W of x. Okay. So we have assumed L of lambda, L of R has simple eigenvalue in L to R. So that means zero eigenfunction of L minus lambda 0 decays exponentially at plus minus infinity. So that means tail part is negative. By tail part, R0 plus phi of plus minus infinity, I mean this part. Okay. So of course, if R0 is too high, too much, then of course the tail part is going to be positive. But we need to have an eigenvalue which has an exponential decay property. So then this tail part should be negative. Since otherwise we may have essential spectrum instability. Okay, so therefore, so the tail part is negative. So then essential spectrum of R is in the left half plane when at the critical, close to the critical point. So in that situation, we can expect a bifurcation of the non-trivial solution occurs at R is equal to R0, and actually we can prove this kind of things really happen in bifurcation theory. Okay, and how about the case where when phi of x is moving with a constant speed? So the difference between the previous equation is here. So that in this case, the environment is moving with a constant speed. And of course, in this case, also we can expect a similar behavior for an appropriate speed. That means a non-trivial positive traveling wave solution bifurcates from W equals 0 at some critical point, R is equal to R0. And of course, this is already studied by Berestiki and Diekman and these people, And in this paper, they studied this program from the different point of view, but this is exactly the same situation of this kind of transcritical bifurcation really happens in this moving environment case. Okay. So actually, so what is this environment phi of x or moving environment phi of x minus ct? So that was our questions. So before constructing this kind of non-uniform environment, we use two-component competition reaction diffusion systems. So this is also the popular fact that if we consider these two-component competition type reaction diffusion equations, we have a traveling wave solutions. But let me be more precise. So the picture, this picture corresponding to the Nuruk line of this ODE part. So the red lines corresponding to the zero set of the first equation, and the blue lines corresponding to the Nuruk line for the second equation. And so these situations are called a strong competition setting because there are two stable equilibriums and one saddle type equilibrium, and of course zero is also the unstable equilibrium. So since by only looking at this ODE dynamics, either E1 or E2 is attained by the stable equilibrium. So this is in some sense I mean, Gauss's explains the Gauss's principles. Okay, and in this case, Cannon proved the existence and the stability of the traveling wave solutions for these equations. And so I drew a simple picture corresponding to the front and back solutions of U and Z. Okay. So I call this, the switching area, I call buffer zone, because here the tail part of U, mostly V is, the winner, but the tail part of V, U is a winner, and only in this switching area, U and V is, making a battle between two species. So let us consider these two component reaction diffusion equations with strong competition, so that we already have a traveling wave solution, capital U of Z and V of Z. And we consider additional equation for exotic species W. Now, of course, W has a similar kind of, the equation for W has a similar kind of shape. Well, let's see, R3 is the growth rate for exotic species W, and B31 and B32 is a interspecific effect coming from U and coming from W, and A3 is, of course, the intraspecific competition rate. And I'm going to consider B31 and B32 is a strategy of exotic species W. Okay, let me explain a little bit more. So W can choose their, interspecific competition rate B31 coming from U and coming from V as they want. So suppose. So therefore, I call this is a strategy for the exotic species. And by choosing appropriately this coefficient B31 and B32 appropriately, is it possible to make a chance to, survive? So that means to satisfy the assumption I already told you. Assumption, so this is do you agree? So it has a similar kind of shape. This one, okay. So as I already told you, so this is the scalar equation, and phi is a moving environment. And if this environment function phi has a nice property, something like this, so then in that case we're going to have an eigenvalue, non-trivial eigenfunction. Therefore, we have a chance to have a bifurcation point, chance to survive. Okay. So, but the shape of this environment function really depends on this B31 and B32. That's why I call this strategy for exotic species. Okay, let me explain it again. So by choosing B31, so how they choose B31 and B32 so that the linearized program of this have a non-trivial eigenvalues, eigenfunctions. So that's the first program. Okay, and here is an example. So by taking the parameters like this, Lee Chan found there is an exact solution like this. Exact solution corresponding to the traveling wave solution with a traveling velocity 1.5. Okay, so So you can check this by the direct calculation. And consider the scalar eigenvalue. Okay. So of course, this is an exact traveling wave solution only considering this two-component system, right? And we also have this equation for the exotic species. So why we have 5/6 or 17/23? But let me tell you later. Okay, but by choosing 17 and 23, this environment function going to have the shape like this blue curve. Anyway, it has a nice area here. And here also, we also have an exact eigenfunction for this corresponding to this. Because to really have an exact eigenfunction, we need to set 5/6. Okay. And so therefore, we have a bifurcation point R0 here. Maybe it's one of the example which satisfy our scenarios. And what is this 50/3? 50/3 is the following. So if we set the growth rate for third exotic species 50/3, Lee Chan also found the exact solution for the non-trivial traveling wave solutions like this. Now, of course, U, Z, and V of Z is original traveling wave solution corresponding to this two-component equation. And by setting 17 and 23 and 50/3 and 5/6 diffusion coefficient, so this is Lee Chan's founding. And this is an exact traveling wave solution moving with the same speed, 1.5. So that means that W exotic species succeeded to survive a little bit only on the buffer zone. Is that okay? So U and V are moving like this. So of course W need to move by the same velocity. But anyway, so they are succeeded to survive only a little bit. So this point, 50/3, corresponding to this point. So, but actually, of course, Lee Chan's this exact solution, Lee Chan found this exact solution before we notice this kind of a bifurcation scenario. Okay, so afterwards we explain why we have a Lee Chan's exact solution. That's kind of strange things at that time. But afterwards we come into this kind of bifurcation scenario. So that's why I think so Lee Chan shed light to this kind of series of research. Okay, and so this example has, actually U and V are independent of W. Okay, so there are no feedback from W, but in general, there could be a feedback back from W. So maybe this is a much more general form to consider the three-component reaction diffusion equations. And now I call this B13 and B23, I call this strategy of the original U and V species. Actually, U can control the interspecific competition coefficient B13 by himself, and V can control, V can choose B23. So therefore, I should call this is a strategy for original species. Okay, so the question is there a bifurcation point for the trivial traveling wave? By the way, I call this trivial traveling wave because capital U and capital V is the original traveling wave solution for the U and V. And if we set W is equal to 0, of course this satisfies this three-component equation trivially. So that's why I call this trivial traveling wave solutions. Okay, the question is, this trivial traveling wave solutions has a bifurcation point still connecting to stable equilibrium, like these kind of exact solutions, even if we have B13 and B23. But in this case, so as I already told you, there is a feedback giving back to U and V from W. So we may expect the bifurcation structure depends on B13 and B23. So these are the basic questions. Okay, let me explain it again. So we first say this B31 and B32 is a strategy for exotic species to really succeed the invasion. So this is the first question. And the second question, so if W has a chance to survive by choosing their strategy appropriately, and the next strategy, so next question is what is the strategy for original species? How they can control the bifurcation structure by adjusting B13 and B23. So actually there are so many parameters. So that's why I explained these kind of things. Okay. So of course we need to consider the eigenvalue problem about W is equal to 0 around the trivial traveling wave solution. So the scalar eigenvalue program for W is going to be like this. So I call this operator L of 3, L3 over R. So we are now on the traveling wave coordinates. So C is the velocity. So I'm sorry I use theta and C for the traveling velocity in the different slides. But so now C is the velocity of the traveling wave. So this is a bit different from the original operator. So I use a kind of this transformation. W is equal to exponential this guy times P. So then this L of 3, the operator L of 3, the eigenvalue program of L3 is equivalent to this equation number 3. Okay, so by this transformation, so that first derivative terms can be vanished. So therefore, we have the similar kind of Schrödinger type operators. And assume L3 of R has simple eigenvalue, or it is equivalent to say M of R has simple eigenvalue in L2R. So this is still an assumption. So then, of course, we need to have an exponential decay. So therefore, we have an essential spectrum of this operator is left half plane. So therefore, we can expect the bifurcation analysis. Okay, and so this is the same thing as I already explained. Okay, but still, this is an assumption. Operator L3 has a simple eigenvalue. Why we can expect this assumption? I'm going to explain this a little bit. At first, we're going to say the traveling wave for two-component system, capital U and capital V, stays below the line connecting E1 and E2. Actually, we can prove this by the simple argument. So the line connecting this one is of course a V star U, and the U star V is equal to U star V star. Now U star is this number, and V star is coordinate value of this point E1. Okay, and actually, traveling wave is of course a heteroclinic orbit from E1 to E2. So then they stays below this, little bit below of this line. Okay. So can you agree the shape of phi of z is something like this? By taking B31 and B32, by taking the ratio of B31 and B32 is this V star and U star. Okay, because E1, so the heteroclinic solution is touching to E1 and E2 at the, both ends. So therefore, phi of z has this kind of shape. And I'm going to explain. This function phi of z has a bound state property in the next slide. So what is bound state property? So I'm not quite sure. The bound state property is a terminology most of the people is using or not. But maybe this kind of things are familiar for the people studying the Schrödinger operators. So of course, this is a Schrödinger operator, eigenvalue program of the Schrödinger operator with potential phi of x. We are interested in this eigenvalue program in the whole line. Okay. And of course, we know under suitable condition of this potential phi, this has an eigenvalue in L2. Do you agree with this? So suppose for simplicity, phi of x is just constant 0. In that case, we don't have eigenvalues. Everything is, every spectrum is an essential spectrum. We don't have eigenvalue. Only phi of x has this kind of shape. We have an eigenvalue. So this is a kind of bound state for the Schrödinger operator. So that's why I call this bound state property. And so the property I call the phi of z is a positive function and exponential decay for the tail. And so that the height is sufficiently high. So then in that case, we can conclude we have an eigenvalue. Why we can conclude this? So you draw these two ordinary differential equation in the two-dimensional system. And of course, this is linear. We can decompose it into, by using the polar coordinate, we can obtain the equation for the angle phi. So this is nothing but a Sturm-Liouville theory. And so that our mission is connect the okay. So suppose first lambda is negative. Then at the tail part, we have one unstable direction and one stable direction for both ends. So our task is to connect this unstable direction and stable direction from -infinity to +infinity. So that's going to be our task. Okay, and if phi is positive phi is sufficiently high, so then this part is going to be negative. Okay. So therefore, totally negative. So therefore we have a rotation around here. So by adjusting lambda appropriately, we can have this. This sort of shooting argument. So this one, starting from the unstable manifold, can really touching to the stable manifold at the +infinity. Okay. So therefore, we can expect this kind of assumption by appropriately choosing B31 and B32. So that's basic scenarios. Okay, and maybe I need to tell you a little bit more detail of the whole linearization of the whole three-component system, but maybe I don't have so much time left. So I just tell you. So okay, by assuming this, I mean the linearized scalar eigenvalue program has really a simple eigenvalue. So by this assumption, we can study the whole linearization. So the trick is, of course, we are dealing with the three-component reaction diffusion equations, but the linearized program of the whole system can be decomposed into two original linearized, two-dimensional originally linearized program plus scalar linearized program, as we already studied. And since we already have this scalar linearized eigenvalue program has a eigenvalue, so that's why we can construct an eigenvalue for the three-component equations. Okay, and let me also notice that in this scalar, in this three-component system, this bifurcation point is going to be a degenerate point because we already have a traveling wave solutions. We already have a zero eigenvalues because the derivative of the solution is going to be the one candidate already is a candidate of zero eigenvalues, and plus we are going to have another eigenvalue coming from this third species. So therefore, we have two degenerate eigenfunctions, and we can conclude that there is two situations: generic situations and non-generic situations. And in generic situations, it's which I call the drift bifurcation. And in that case, we have one eigenfunction phi of z, and psi of z is going to be a generalized eigenfunctions. And we can construct the same kind of thing for the adjoint operators. And in the case of non-generic case, in that case, we really have two eigenfunctions. Okay, and we can construct a bifurcation theory corresponding to these degenerate situations. And but let me show you a little bit numerical simulations before going to state the bifurcation theorems. Okay, we are going to use similar parameters as I already told you. Okay, and of course taking this the growth rate of exotic species as a parameters, but of course in this case we have an exact solutions. Okay, so so here is a numerical continuation of this bifurcation program. And okay, let's look at the right pictures. So this is a profile of the function W. Okay, so let me say something before going to the right pictures. So, okay, so the left pictures and the right center pictures, you see the red lines. So this is a trivial traveling wave solutions. Okay, so left pictures I denote the velocity of the traveling wave solutions, and as I already told you, our original traveling wave solution has a velocity 1.5. So therefore, this red line is a trivial traveling wave solutions. And the number 7 point may be a bifurcation point. Okay, and the center picture I showed you a L2 norm of the W plus 10. So if I use just a L2 norm of W, so then the bifurcation pictures does not look like transcritical bifurcation. So that's why I use W plus 10, L2 norm of W plus 10 instead. Of course, the number 10 does not have any special meaning. So plus 1 or plus 20, that doesn't matter. Okay? So, but anyway, so if you look at this L2 norm, you can see that 0.6 and 0.5 and 0.4 corresponding to the positive solutions. W, the shape of W is the positive solutions. Number 4 actually corresponding to this black. Maybe you cannot distinguish which one is number 4 and 5, but this black curve corresponding to number 4. Okay, and at number 7, the shape of W is almost 0. And 8 and 9 and 10 is a negative solution for W. Okay, but if we look at only center pictures, we can understand the situation without looking at right pictures. Okay, but the center picture is not enough to understand everything because the velocity is not always positive, but I mean the speed up or speed down. By speed up, I mean original traveling speed is 1.5. So that means in this case, after the bifurcation occurs, these positive W solution, the speed of the these kind of solution is a bit higher than original 1.5. So that's why I call this speed up situation. Okay. So so this first picture I showed you, that corresponding to the case where B13 and B23 is both 0.5. So what was B13 and B23? Let me go back again. Here, okay. So B13 and B23 is a strategy for the original species. So maybe they can control the bifurcation structures. So anyway, the bifurcation occurs. It's inevitable by W. So if W has a suitable strategy, B31 and B32, so then the bifurcation may be inevitable. So the next thing U and B can do is adjusting B13 and B23. So that's why this strategy for original species is also important. Okay, and so that's why we are going to see this. So in this case, sort of a supercritical bifurcation occurs, and by that bifurcation, the traveling wave velocity is going to be a little bit higher. Speed up occurs in the case of 0.5 and 0.5. Now, we take several different set of parameters B13 and B23 as I show you in these pictures. So from now, we are going to see what happens. Say, for example, the case 1. So if I change from G1 and in between, so this one is N1, G1, N2, and D2. And what happens, say, in the case of 2, G4 and N4 and G7, and number 3 and number 4. So let's look at what happens by changing B13 and B23. So this 4 selection is a kind of typical situation. So that's why I showed you. Now, G1, N2, G2. So left pictures for upper row and lower row are corresponding to the G1. And the middle row, middle case, N2 and G2. So what was G1, G1, N2, G2? So this one here, okay? Only a tiny change between B23. G1 is 0.6, and N2 0.635, and G2 0.7. only a tiny change, but the result is very different. Okay, so if you look at the L2 norm, we always have a supercritical bifurcation. By supercritical, I mean we have a positive non-trivial solution after R is larger than critical point. Okay, and from left, speed up situation, and while the right case, speed down occurs. You see? So that's the reason why we need to look also C and L2 pictures. Now, what happens in the case 2? At G4, N4, G7. So now what's happened? Okay, if you look at first L2 norm pictures, so then we can conclude all of these are subcritical situations. That means we have positive non-trivial solutions by this bifurcation when R is below the critical number. So that's why I call it subcritical. Okay, all of them are subcritical. And if you look at the speed, in the left case, speed down. In the right case, speed up occurs. So where was D4, N4, D7? D4, N4, D7 here. Okay, so look at the case 3. We need to compare G5, G8, G9. So in this case, G5, G8, G9. In this case, we have a supercritical situation at G5 and a subcritical situation at G9. And so of course, in between, we have a pitchfork bifurcation case. All of them are speed up occurs. And in the case of 4 like this. So how we can understand this? So I already used most of my time. So I just tell you the result by using the center manifold theory, by using that kind of degenerate eigenvalues, degenerate case. So anyway, so since we have 2 eigenfunctions or 1 eigenfunction plus generalized eigenfunction. So anyway, in that case, we are going to have a bifurcation equation for this 2-dimensional. So we can characterize the center manifold dynamics very close to the bifurcation point by just looking at these 2-dimensional bifurcation equations. And we can actually calculate all the coefficients theoretically, but of course they are very complicated. And so here is a summary of the generic case and non-generic case. We have a little bit different bifurcation equations, and of course there are several constants, but the essential constant is so let's look at the equation for theta. So theta control something like an amplitude of the bifurcation solution. So that's why the first thing we need to look at is the equation for theta. Okay, and eta is a bifurcation parameter. So therefore, if M1 is positive, so then we are going to have a supercritical, transcritical bifurcation. While the M1 is negative, we are going to have a subcritical type transcritical bifurcation, something like that. And by discussing these kind of things, we can maybe, so these are so complicated. So I just going to show you the picture of this. So these points on the, so actually this is a B13 and B23 plane. similarly to the previous slide. And all of these points, as I already show you, we already check what happens number 1 case and number 3 case, number 2 case, and number 3 case, and number 4 case. Okay, and this slide coming from the positivity and negativity of the sign of C1 and the M1, and we can conclude the bifurcation structure corresponding to this positive and negativity. Let me tell you a little bit. So at first, in this B13, B23 plane, this blue line corresponding to the non-generic case. Okay, only on this line, we have 2 different eigenfunctions. But except on this line, we are going to have a generic situation. And in that case, we have a drift bifurcation. That means we have one eigenfunction and 1 generalized eigenfunction. And we can use bifurcation equations, and we can conclude that after the bifurcation occurs, in these red regions, the bifurcated traveling wave solution is a little bit high, has a little bit high velocity, while here, blue region, the spill down occurs. And if you calculate the positive and the negativity, and there is another line here, which says which divides this B13, B23 plane into 4 parts, and here the M1 is positive, and here M1 is positive, and this one is negative, and that can conclude only on this line Hitchcock bifurcation, of course. So anyway, so by looking at this, we can conclude that by choosing B13 and B23, so that's a strategy for original species, so they can control the bifurcation structures. Okay, so so here is actually the schematic picture for the bifurcation structure by just looking at the in this division coming from the sign of M1. Okay, and so here is a reference of these kind of topics. And quite recently, Shunshin-chan and Chun-chan Chen and Lee-chan and Mimura-san published a paper relating on this topic, but not the bifurcation structure, but I mean the kind of perturbation result of this kind of things. Okay, so I consumed time, so thank you very much for listening to my talk. Thank you.
Thank you. Thank you for your nice talk. So any question or comments?
Oh, may I have a question?
Okay.
So thank you very much for your wonderful talk. Yeah. Your explanation is really very nice. Yeah. So I have a question that so could you go back to page 42?
42, okay. Can you see this?
Yes, I can see.
Shall I expand? So it's still okay?
Yeah, still okay. Yeah. So for the left picture, so you mentioned there is a borderline between the region of speed down and speed up.
Yeah.
So is the borderline really a straight line?
So this is actually the non-generic line. So if you choose this, if you choose a parameter only on this line, so
yes,
of course the bifurcation, I mean, equation is different.
I see.
But I mean the result, of course, consisting between generic case and non-generic. But anyway, so this is generic case. Let me tell you a little bit more. Of course, this is coming from the signs of C1, and if I tell you a little bit more detail. So,
Yes.
so here is a sign of C1. And for
Uh-huh.
example, if you, so this right picture corresponding to the graph of C1 by just setting B to 3 is 1. So that means that if you see the cross section here, so then the shape of C1 is like this. So that means that if you coming very close to this border line, of course the sign of C1 is positive, but going to diverge. And if you come close to this borderline from left, so then it's negative and diverge.
I see.
So this kind of things happened because we need to analyze the dynamics separately on this borderline and another part. Because this is a generic case and non-generic case. But if you carefully study the bifurcation analysis, of course the result is consistent between this and this. So that kind of situation happens. So this is already a complex.
Yes. Yeah, very complex. So the condition to determine the borderline is a linear relation?
Yes.
I see.
That comes from so this is a generic condition, and so if you so as I already told you, the operator for 3-component system can be decomposed into 2-component plus 1, and so that means that we need to solve the 2-component problem by just substituting. So we first solve scalar eigenvalue problem, and then we plug this back to the 2-component linearized problem. So anyway, we need to solve this. So this borderline comes from a solvability condition for this. So in the case of solvability condition holds, we have a non-generic situation, and the solvability condition does not hold, so then we have a generic situation. So that's why the linear. So this coming from the linearized.
So that's very nice.
Yeah.
So for the condition for the pitchfork bifurcation is also a linear relation.
Okay. Let's see. So that coming from a center manifold theory, and the pitchfork bifurcation. So this is of course a bifurcation equation, and so the pitchfork happens when M1 is equal to 0.
I see.
Okay, but M1 is very complicated. I just write beta, but beta is very complicated coming from. But we need to use adjoint eigenfunctions and everything. So of course I calculate this by using numerical calculations. So of course this kind of picture obtained by calculating that coefficient numerically. But still very consistent with Otto's numerical simulations. So that's why we believe we may generically have this kind of situation. You
so
see,
this picture are really very good.
This is very interesting because why the pitchfork line is really line? Maybe there should be some reason.
I see.
But I don't know why this happens.
Oh, that's very interesting. So thank you very much.
Thank you.
Thank you. So you are going to leave right now? 3 minutes? 2 minutes?
2 minutes.
2 minutes. Okay. Well, may I ask one quick question? So in your bifurcation, at the beginning you choose the speed. It's a trivial traveling wave with speed 1.5.
Yeah.
So if now you choose a trivial solution with 0 speed, then can you do the denting for this bifurcation?
That's really a nice question. And you see, maybe my computer is not good. Okay, so in this case, of course, this is not symmetric. So that's why the traveling wave is moving 1.5.
Yes.
But I mean, the competition is really symmetric. In that case, of course, the traveling wave is just stationary solutions. Okay, so in that case, I believe this picture is going to become very symmetric. Okay, this borderline is going to be 45 degrees, and this pitchfork line is just like this.
I see.
Why I didn't show you this? Because I don't have exact solution for that symmetric situation. So I can calculate this very accurately, because we have 2-component exact solutions. I mean, the theory is of course true for all cases. But if we really like to calculate this kind of pictures in the symmetric case, we don't have an exact solution. Of course, we need to use numerically calculated solutions. But by that, the accuracy program happens. And maybe I can, but I'm not trying. But
okay,
the accuracy is
thank
not
you.
good.
Okay,
So
thank you.
Lee-chan's exact solution is always, useful, even in this case.
Okay, thank you. So we are very sorry because the Ogawa sensei have a meeting, so he need to leave now. So let's thank the speaker again.
Thank you.
Thank you.
And maybe see you in the near future.
Yeah, thank you so much. See you in near future.
Yeah, see you. So
Thank
bye-bye.
you. Thank you.
Bye-bye.
Thank you.
Bye-bye.
Bye.